What if I told you that the universe is held together by something we can't see, can't touch, and can't feel? It's probably one of the biggest and, frankly, strangest puzzles in all of science, and today we're going on the hunt to find it. This is the story of dark matter.
Right, let's just kick things off with this absolutely mind-bending fact. When astronomers look out into the universe and they add up everything, and I mean everything we can see, all the stars, galaxies, planets, gas, the whole shebang, it turns out all of that only accounts for about 15% of the universe's total mass. A staggering 85% of all matter is just gone, missing.
And that leads us to the central question, doesn't it? If 85% of the stuff that should be there isn't, well, where is it? Think of this as a cosmic detective story. We're going to follow the clues and track down this invisible culprit.
Now, the first clues in this case didn't come from some supercomputer or a high-tech satellite. Nope. They came from astronomers way back in the early 20th century. They were the first ones to look at the evidence and realize something was fundamentally wrong with our picture of the universe. They were the first detectives on the scene of this cosmic crime.
It all started back in 1933. An astronomer named Fritz Zwicky was looking at the Coma cluster of galaxies, and he saw they were moving so fast they should have just flown apart. So he proposed this wild idea of an unseen dark matter holding them together with its gravity. But honestly, nobody really paid attention for decades. Then, in the 1970s, Vera Rubin just blew the case wide open. See, she expected stars on the edge of galaxies to move slower than the ones in the center, kind of like how Pluto moves slower than Mercury. But they didn't. They moved just as fast. The only way that makes sense is if the entire galaxy is sitting inside a massive, invisible halo of this dark matter. Her data was just undeniable.
Okay, so we have a suspect. The next step in any investigation, right? You build a profile. What exactly is this dark matter? What does it do? What are its habits? Let's take a look at the evidence.
You know, the easiest way to get your head around dark matter is to start with everything it isn't. First off, it's not made of atoms, not the stuff that makes up you, me, planets, stars, anything we know. And it doesn't interact with light at all. It doesn't glow, it doesn't cast a shadow. That's why we call it dark. It's not just dim, it's fundamentally totally invisible to all of our telescopes.
And to really understand just how weird this stuff is, think about this. The leading theories suggest that these dark matter particles are so ghostly, so non-interactive, that they could stream right through your body and through the entire planet without ever bumping into a single atom. It's like we're living in a constant shower of cosmic ghosts.
So who are the main suspects in our particle lineup? Well, physicists have a few prime candidates. For a long time, the favorite was something called a WIMP, a weakly interacting massive particle. Then you've got axions, which are these theoretical particles that would be incredibly lightweight. And then there are even more exotic ideas, like sterile neutrinos. We have no idea which one is right, but these are the guys on the most wanted list.
But here's the thing you absolutely have to understand. Even though it's invisible, dark matter isn't just floating around doing nothing. It is the literal scaffolding of our universe. Its immense gravity is what pulled matter together to form the first galaxies, and it's the cosmic glue that holds them together today. Without it, the universe as we know it would just fly apart.
Now, the theory is really compelling. But how can we be so sure this stuff is real? Let's dig into the hard evidence and see how this global manhunt for a single ghostly particle is actually going down.
One of our best tools is something called gravitational lensing. Basically, Einstein figured out that massive objects literally bend the fabric of space and time around them. So light from a distant galaxy will actually get warped and bent as it passes by something massive. Here's the cool part. By measuring how much that light bends, we can weigh the object that's doing the bending, whether we can see it or not.
And that technique gave us our smoking gun. Back in 2006, astronomers watched two entire galaxy clusters collide. The normal, visible gas clouds, all the pink stuff you see here, smashed into each other and slowed way down. But when they used gravitational lensing to map out where the mass was, they found that most of it, the dark matter, sailed right through the collision like it wasn't even there. It was the first time we'd ever seen dark matter and normal matter so clearly separated. Just incredible.
And look, it's not just one thing. The evidence is just overwhelming, and it comes from completely different lines of investigation. You have Vera Rubin's galaxy rotation curves, you have the gravitational lensing maps we just talked about, and even the faint afterglow from the Big Bang itself, the cosmic microwave background, they all point to the exact same conclusion. The universe is filled with dark matter.
So how in the world are we trying to find this stuff? Well, the global search is basically happening on three fronts. First, we try to catch it. We build these incredibly sensitive detectors deep underground, shielded from all other radiation, just waiting for that 1 in a trillion chance that a dark matter particle will finally nudge one of our atoms. Second, we try to make it. At giant particle colliders like the one at CERN, we smash particles together at insane speeds, hoping that some of the energy from the collision disappears into a newly created and invisible dark matter particle. And third, we try to see its effects. We use space telescopes to look for strange signals from space, like a mysterious glow of gamma rays that could be the signature of two dark matter particles annihilating each other.
Okay, so this is a massive, incredibly expensive global effort, which leads to the big question, why? Why does finding one invisible particle matter so much? Well, the answer is pretty profound. This isn't just some random particle, this is the ghost that built our cosmic home.
This chart right here, it really puts it all into perspective. Everything we've ever seen, ever touched, ever known, every star, every planet, you, me, all of it is just that tiny little 15% sliver. We live in a universe that is completely dominated by a substance we don't understand at all. We aren't the main event. We're the weird stuff. We're the exception. Solving this means figuring out what the other 85% of reality is actually made of.
Let's make this really personal. Right after the Big Bang, it was the gravity of dark matter that pulled the first tiny wisps of gas together, creating the seeds of future galaxies. Without those gravitational seeds, our own Milky Way galaxy would never have formed. Without the Milky Way, our sun would never have been born. And without our sun, well, there'd be no Earth. The conclusion is just inescapable. Without dark matter, we would not be here.
So ultimately, this hunt is about so much more than finding just one new particle. You see, our best theory of, well, everything is called the Standard Model of Particle Physics. It perfectly explains all the known particles and forces. But it has absolutely no room for dark matter. It doesn't fit. So finding dark matter means we've found something fundamentally new about how reality itself works. It's the key that will unlock a whole new chapter in our understanding of the cosmos.
And that's really the question we're left with, isn't it? The hunt is on. Every year, the experiments get more and more sensitive. We are getting closer to finally meeting the ghost that built and inhabits our universe. And when we finally do, what new, incredible physics will we unlock? What secrets about the cosmos will it finally reveal to us?